should be posted. Yep, I think I have them here. They'll be posted by noon tomorrow. Another question?
I was just gonna say, I think I saw like test 1B from 2017.
Right.
I only saw like the answers. I'm like, are you gonna post a test also, or?
No, maybe. Was that the last one?
Yeah, it was the most recent.
I think that was just the equations, actually.
Okay.
So, yeah, I should be able to post more. I don't necessarily have answers readily posted, but if you could send me an email.
Okay.
Other questions? So I'm not quite sure of how many to post, because for 110, I probably posted more tests than any other class. And sometimes I think students look at that and they suddenly say, oh my gosh, I've got 20 different tests I can look at, and it overwhelms them. So I'll be glad to overwhelm you if you want.
Yes, do.
All right. Any other questions at the moment? Precious?
Yeah, on the old test, I think this is fall 2013. I just didn't understand what this question is.
Right. Oh. Was the period? All right, so this is the Oak and Bucket question, or a variation of the Oak and Bucket question. So you have the room here, and you're up against the side. That's an arm stretch out like that. So the forces acting on the person. We have normal force this way, we have friction acting up, and we have mg acting down, or weight. And so I know the normal force is equal to mv squared over r. And so if I black out at 4 g's, that means I'm experiencing acceleration of 4 times 9.8 meters per second squared. And so you're looking for v squared over r, or omega squared r, depending upon your mood, equal to 4 times 9.8.
Okay, so that's one.
So then you would find the speed, and then from that you can find the period. Is that sufficient?
Yeah.
Okay.
Okay.
Mhm. Any other questions? All right, let's pick up where we left off. Now we found, let's use the same numbers, and I don't remember what they are. So I had 2 objects heading towards each other. The one on the left, what was the mass and initial velocity?
5 kilograms and 3 meters per second.
5 kilograms, 3 meters per second. And the left one?
4 kilograms, 6 meters per second.
And 6?
Yeah, 4 kilograms, 6 meters per second.
This is what I wanted right now, but let's nitpick some of the language I just used. One of those is incorrect, given the question I actually asked. And it was not my intent to trip you up and just using this as a moment. Because I asked what's the velocity of them.
Negative 6 meters per second.
Yeah, one of them's gotta be negative. So since Max spoke up first, we're gonna establish to the right as positive. And I'm just gonna call this mass 1 and velocity 1 initial. And this is mass 2 and velocity 2 initial. In nice tiny print so that anyone who's watching the video later will have to wonder what I just wrote. And just because I don't like writing subscripts, I'm gonna do one other step. I'm just gonna use the letter A to represent that velocity and B to represent that velocity, or actually B is -6 meters per second. And A is 3 meters per second. It's one-dimensional motion, so I can get away without using I hat and J hat. Right, so we went through the long way, we ended up with a quadratic. It had the definite benefit of the fact that one of the solutions was the non-collision solution. And so let's take a look at a different way of solving it. I'm doing it in generic terms here. So I know my initial momentum is equal to my final momentum. Conservation momentum. So this is equal to M1 A plus M2 B. And that should be equal to the total momentum after the collision. And so I'm going to use the letter C and D, and let's just go ahead and define it here officially. C is V1 final, and D is V2 final. I think I used C and D last time also. So this would be equal to M1C plus M2D. We know all the numbers in this equation except for C and D. We don't know what they are officially, even though we have solved it already. Now we're doing a one-dimensional, perfectly elastic collision, so one-dimensional, perfectly elastic collision. The collision tells us momentum is conserved. What's the perfectly elastic mean? Yes. Oh, we can do it. Yes. Another opportunity. Here we go. What's the formula for kinetic energy?
1/2 mc squared.
That was nice. Nice. So 1/2 mass 1a squared plus 1/2 mass 2b squared equals 1/2 mass 1c squared plus 1/2 mass 2 times d squared. So I have my two equations here. Again, the collision is giving us this. This is the conservation of momentum, conservation of momentum. And the perfectly elastic is giving us this conservation of kinetic energy. Again, I know what M1 and M2 are in the problem. I know what A and B are. I don't know C and D. In essence, I have two equations, two unknowns. Therefore, it is solvable. Well, one would hope. So let's solve it. So to solve it, we need to simplify it down a little bit here. So we have this, I can get rid of the 1/2. Just multiply the whole thing by 2. And now I'm going to get sort of the M1s together. I'm going to group them so all the mass 1s are on one side and all the mass 2s are on the other side. So my first equation here becomes M1A minus M1C is equal to M2D minus M2B. And then down there we have M1A squared minus M1C squared equals M2D squared minus M2B squared. Now let's do some factoring. We can factor M1 out of the left-hand side in both equations. So I have M1A minus C is equal to M2D minus B. And for the second equation, I have M1A squared minus C squared is equal to M2D squared minus B squared. Of course, we can factor that second equation again. How do you factor a squared minus c squared?
A plus C, A minus C.
Yep. So that second equation becomes m1, a plus c, a minus c. And that's going to be equal to m2, d minus b, d plus b. Now the math people, I'm assuming they're not lying to me or have not lied to me, that if I divide both sides by the same thing, I'm good to go. So what I'm going to do is I'm going to divide the left side here by m1, a minus c. And the right hand side, I'm going to divide by what's equal to it, just m2, d minus b. The denominators are equal, as shown from my momentum equation. Now I can cancel some stuff out. The m1s go away. The a minus c's go away. m2 goes away. D minus b goes away. And I'm left with a very nice a plus c is equal to d plus b. Now, the a and the c are the velocities of mass 1 before and after. D and b are the velocities of mass 2 after and before. So let's get the initial stuff together and the final stuff together. So in other words, bring b over to the left side and c over to the right side. So if a minus b is equal to d minus c. Or putting in the more formal language over there, V1 initial minus V2 initial equals V2 final minus V1 final. Let's think about what this is. This notation right here is saying what is the velocity of object 2 with respect to 1? Let's see, do I want to do it that way or reverse it? Actually, I want V1 too. The velocity of mass 1 with respect to mass 2. In other words, if you're sitting in mass 2, how fast does it look like mass 1's coming at you? By just property of vectors, that would be the mass velocity of 1 with respect to L. This right here, in the initial situation, this is sometimes referred to as the lab frame. Or the problem frame, or however you want to word it. This is just some reference frame where we're looking at these two things heading towards each other. I'm just going to call it the lab frame. So the velocity of 1 with respect to 2 is equal to the velocity of 1 in the lab frame plus the velocity of the lab with respect to 2. Again, the vector addition works as long as these two are the same. So this is the velocity of 1 in the lab frame, in other words, letter A. And here, I'm going to switch the viewpoint around. So instead of the velocity of the lab with respect to 2, what's the velocity of 2 with respect to the lab? And when I do that, I have to change the sign. So that's minus the velocity of 2 with respect to the lab. and this is all initial. Or before the collision. In other words, this is just A minus B.
Dr. Fox,
Yes.
would the lab frame be the non-inertial reference frame or the inertial reference frame?
It would be an inertial reference frame, it's just not, it's not from the point of view of anything personal in the problem. Meaning that it's not from the point of view of, it's not from mass one's left point of view, mass two's left point of view, or the center of mass's point of view. Since this is the velocity of one with respect to two, this is, if you imagine that you are sitting inside mass two, how fast is mass one coming at you? So this is known as the relative speed of approach. After the collision. Oh, sorry, before we do that, pause for questions. Right. So afterwards, the velocity of 2 with respect to 1, because I know where I'm heading with this. So this is velocity 2 with respect to the lab frame, again, after, plus the velocity of the lab frame with respect to 1. The same process we had over there. So that would be equal to the velocity of 2 with respect to the lab frame, minus the velocity of 1 with respect to the lab frame. And again, since this is after, that would be d minus b. So this is v2f minus v1f is the relative speed of recession.
So basically they're equal, but the reference frame changes.
Yeah, I think that's legitimate. We'll apply it in just a moment. So we now have a second method of solving the same equation here. So let's actually take a look at it. So momentum's conserved. So we have 5 times 3 plus 4 times negative 6 is equal to 5c plus 4b. This is just the conservation of momentum equation. This, we would have written this up yesterday also. The second equation, Thursday, we did the conservation of kinetic energy. We don't need to do that anymore because we have an alternate variation based upon it. And so we have 3 minus negative 6 is equal to d minus c. No quadratic formula needed. So that makes 9 is equal to d minus c, or d is equal to c plus 9. Plug that into here. I have negative 9 is equal to 5c plus 4 times c plus 9. Negative 9 is equal to 5c plus 4c plus, doing the fancy math here, 36. Negative 9 is equal to 9c plus 36. 9c is equal to negative 45. Negative 5 meters per second. And we have a formula for d right here, so this becomes negative 5 plus 9, which is 4 meters per second. And I'm hoping that's what we got when we solved this on Thursday. So after the collision, so this is before, after the 5 is shooting back at 5 meters per second. And the 4 is shooting to the right at 4 meters per second.
I might have wrote it down wrong, but I got C more than 3 the last time I did.
All right, so did I get a minus sign messed up somewhere? So 3 minus,
I think I got 4 meters per second.
pardon?
I think I got 4 meters per second.
Last time?
Yeah, is it, for D minus C?
So D minus C should, are you pointing to, that's that where you did the work?
That's,
That's what we did last time.
yeah.
Okay. 4 and 5, okay. And you had written down last time? Huh. Oh, there were the 2 solutions there. That 3 was that they never actually hit.
Oh, okay.
If you do it that technique, one of the solutions should be the non-collision solution. And that's, so, since there is a collision, that's the one that we don't do. Right. Way to worry me there, Kyle. Right. So questions to hear?
But basically, this is a safer way to do it, because then you don't have to deal with, like, guessing which ones, they're not guessing, but identifying which one's the right of the 2.
Well, the advantage of the first way is that one of the solutions will be they didn't actually collide. So one of the solutions should have been, doing the technique from Thursday, should have been 3 and -6. So that's definitely a plus for that. To me, the advantage of this is we're not dealing with the quadratic formula. The more I have to write down, the more likely I am to make a mistake. So you make the call for you, which one you like. I'm gonna do a third method also, which is my personal favorite, but not everyone likes it because it's slightly more abstract. Again, this is for the one-dimensional perfectly elastic collision. Please do not apply this to two-dimensional problems or one-dimensional imperfect or perfectly inelastic collisions. All right. Method number 3. You're gonna know what the answer's gonna be. So let's, in our lab frame, we have the 5 kilogram mass is going to the right at those 3 meters per second, and the 4, -6 meters per second. Those are the velocities in the lab frame. And the total momentum becomes 15 plus -24 or -9. Let's make this meters per second. All right, so this is us standing by, we watch these 2 things go. Now suppose instead of just standing to the side, we decide to move. So as this thing is going on, I'm moving along at 3 meters per second to the right. So if I am moving at the same velocity as the 5 kilogram mass, how fast is it going from my point of view?
Not
So if I'm going to the right at 3 meters per second frame, this is not moving. How fast is the 4 kilogram mass moving?
So would it only be like negative 3 meters per second in that direction?
It would not be negative 3. All right, so let's think about it from a different point of view. So right now, in the lab frame, it's coming towards me at 6 meters per second. If I start moving towards it, is it going to be moving faster or slower than 6?
Faster?
Yeah, so negative 3 meters per second would be a slower speed for it.
So -9?
Negative 9. And so this would be, so the momentum in this reference frame would be 0 plus negative 36, or negative 36 Descartes. I should be able to shift reference frames and the physics should still work. There's no absolute reference frame, so there's no reason why, the lab frame is special other than that's what the problem was given in. Suppose I move to the left at 6 meters per second. How fast is the 4 kilogram mass going now?
Not moving.
How fast is the 5 kilogram mass moving?
18 meters per second.
18? How'd you get 18?
I'll multiply 6 times 3, but that doesn't make sense because that was for the lab frame. So multiply 6 times 5.
Not quite. Pardon?
Is it 9?
It's 9. We'll get the pattern in just a second. So my total momentum now is 9 times 5, or 45, plus 0, or 45 Descartes. So all I'm doing when I'm shifting reference frames is I'm just adding or subtracting from the velocity. So here, I'm moving at 3 to the right. I did I did 3 minus 3. To get this one, I did 3 minus negative 6. Where that 3 comes from, how fast it's going in the lab frame, and this, then I subtract whatever that is. This would be negative 6 minus 3, again, subtracting 3 both sides. And then negative 6 minus negative 9. Let's try that again. Negative 6 minus negative 6. So explaining that, if I move to the right at 2 meters per second, what will this be? How fast is the 5 kilogram mass going in this new reference frame?
1 meter per second?
Yep. 80 units there. And this one?
-5 meters per second? Or excuse me, -7 meters per second?
Or? This was 3 minus 2.
Negative.
Oh.
Negative.
Negative.
You said 8?
Yeah.
Yes. Negative 8. Negative 6 minus 2.
Oh.
So the momentum in this reference frame is 5 minus 32, which is negative 27. Questions about just shifting velocities based upon different reference frames? All right. I hope you can see that I can just manipulate whatever I want my total momentum to be just by changing my reference frame. So what I want to do is I want to figure out where in what reference frame is the momentum equal to, total momentum equal to 0? Since all I'm doing is subtracting the velocity of however fast I'm going over there, I can set this up easily enough. So it's the mass times the velocity, so that's just going to be whatever its initially is, minus my reference frame speed, velocity, plus 4 times -6 minus v equals 0. Because I want 0 to be my total. So this is 15 minus 5v minus 24 minus 4v equals 0. -9 minus 9v equals 0. Double check that. I go to the left at 1 meter per second. My velocity of the 5 kilogram mass will be 3 minus -1, or 4. The 4 kilogram mass will be -6 minus -1, which is -7.
Is that -5?
Yes, it is. Thank you. So my total momentum is 4 times 5, which is 20, plus -5 times 4, which is -20. So potentially the downside of this is it's a little bit more abstract thinking. You have to be able to picture it moving in a different reference frame. We're not done yet. This is the hardest part of it. Now, if you flip back through your notes, we had -1 meter per second. We actually had that as an answer for one of the problems that we did on Thursday. What was the problem?